Hello everyone, welcome back. So in the last couple of lectures we looked at photon statistics. We said that if light exhibits the quantum nature, light is a stream of photons, then what does it mean? When you have, what sort of statistics will it show when you have perfectly coherent light, and what happens when you have incoherent light, that is thermal source as an example. And how can you achieve even quantum light, that is Sub-Poissonian statistics, right? So today we will, in this lecture, we will talk about some of the practical issues in actually studying this. Okay. The first issue I want to talk about is what happens when you have losses. All right. So for example, let's say I have a light beam which is incident on a lossy medium. So here, let's say there are 100 photons that are incident on this medium. How many photons will get transmitted? That's a question. So we know, we have studied this in the beginning. So the transmission is going to be 100 photons times exponential minus alpha L, where L is my length of the medium and then alpha is the absorption coefficient. Okay. So what we are seeing is basically the photons are getting absorbed, but which photons are getting absorbed? That's an important problem. The reason is the absorption process is random. If it is random, we can never, if you have a stream of, let's say 10 photons, we can never predict which of them are going to get absorbed. And invariably, the photon statistics are going to degrade. Okay. So let's understand it this way. Let's assume that there is a perfect Sub-Poissonian source. So that means I have a stream of photons which are equally spaced in time. Okay, they have this stream of photons. This is a perfect Sub-Poissonian source. Poissonian source. That means I have the fluctuations in the photon number. So we have the average photon number we talked about, and then the fluctuations are basically delta n. Let's assume that if it's a perfect Sub-Poissonian source, I have my delta n to be 0. Okay. Now, what happens if I send this light through a medium with some loss? Okay, let's assume initially there is some small loss. What do we expect? What is the output, right? So, of course, some of the photons are going to get absorbed as they propagate through the medium, right? So now, let's take this and let's say that we have managed to put it through the medium, and because of some small loss, let's say 2 photons are absorbed now. So what will be the statistics of this? Now, if just a few photons are absorbed compared to the overall incident photons, then your statistics are still going to be Sub-Poissonian. Okay, but now your fluctuations delta n are not going to be 0, but it's going to be something slightly greater than 0. So let's say that it is still, for small losses, it is still less than the average photon number. It's between 0 and average photon number, so it will still be Sub-Poissonian statistics. But what happens if you have large amount of loss? If I have large loss, okay, then my photons might be, a lot of photons might be absorbed, and eventually you might end up with just, let's say 3 photons like this. Okay. So in this case, now the fluctuations are much larger than the initial incident beam. So your delta n is going to be larger than the average photon number n1. So we can clearly see that if you have losses, that can degrade the statistics. So one of the conclusions we want to make here is that optical loss degrades photon statistics. What do I mean by that? Well, even if you have a perfect Sub-Poissonian source, the presence of optical loss will actually make it Super-Poissonian or Poissonian. Okay. The same thing is illustrated here. And in general, what happens is in the community, we use what is known as a beam splitter model for modeling loss. So loss, what we will do is we'll have, let's say, a light incident. I'll say there is a beam splitter. A beam splitter is simply a device which splits the one beam into 2 parts. Let's say some of it is transmitted, some of it is reflected. Okay, so in this case here, let's say the transmission coefficient is t, so that many photons are going through, and then the rest of them, the 1 minus t photons, are actually going to the other side. Okay, they're getting reflected. So this is a beam splitter. So this can be used to model as a by a beam splitter. Loss is modeled by a beam splitter. So now you see that clearly there is this stream of photons which are incoming, which are very, very perfectly arranged with equal spacings. But the moment you go through the beam splitter, some of the photons are going to the port 1, which is this, they're getting transmitted, and the remaining photons are absorbed. So in this case, we are just showing it by, or this is basically absorbed photons, right? We are assuming that there is no reflection from the beam splitter. So the way to create a beam splitter like this is also a challenge. We can do it with photonic crystals ideas. Okay, so this is how practically the photo detection itself makes it challenging to observe Sub-Poissonian statistics. So the question was, your beam splitter, one part of the beam is actually getting reflected, and some of it is traveling through. Now this beam is actually going through the medium, and will that not affect the statistics going through the beam splitter? Well, it will. That's why we want it to be low loss. The beam splitters, we don't, zero loss. Essentially, we use something like a glass at a perfectly defined angle. It will actually transmit and then reflect, but not absorb. But then you should also make sure that the beam splitter is not very thick. Again, that will cause some refraction effects and things like that. But what happens to a photon when it passes through a different index medium? We understood what happens in the wave picture. The wave fronts will get compressed, right? Or rather, the phase fronts will get compressed. But what happens in a photon picture? Well, I mean, the spacing between the photons should reduce, right? That's what should happen here.
So that will kind of, if you are looking for,
but then it's again uniform. It's not a, it's just refractive index, right? But again, when it goes out,
again it will change.
yeah, the frequency should not change. So that's a question mark. I mean, we'll have to think about it a little deeper. We remember when we talked about the frequency, the frequency doesn't change. So if you say that, let's say the photon distance is reduced, if you say that, then when it comes out, how will it again expand? If I define my frequency as the rate at which the photons are coming, that should not change maybe. It's something that we'll have to look deeper. Yeah. The photon picture of actually transmission through a medium. What happens at the interface between two media in the photon picture, we'll have to look deeper. Yeah. All right. But if you think of frequency as something which is simply oscillating, I mean, the time period between the photons, right? Then that should not change, because the regularity has to be maintained, because the photons are actually coming from somewhere else. The source is going to determine the frequency. The rate of emitting single photons, let's say. Rate of emitting of photons. If I talk about that, let's say there is a rate at which it's getting emitted, and then if they're not getting absorbed, just because I put a glass in between, will the rate change at the end of it? It shouldn't. The rate should remain constant. So what changes as it passes through? What property of the photon changes as it passes through the slab? Is I mean, we understand there is some dispersion. We'll have to look deeper actually. Yeah. Okay. Right. It's a very, very thoughtful question. Yeah. Thank you. All right. So yeah. So what happens, when you are trying to detect a photon, right? So we talked about the photodetector, and we sort of said that, okay, we just need a high quantum efficiency photodetector, and that is enough, right? But it turns out that it's a little bit deeper than that. In fact, in the beginning of quantum optics, there was a lot of debate about whether the statistics that we are observing are actually the property of the source or the photodetector. The reason for that is, let's assume, if you assume a perfect, assume a classical EM wave, okay, of constant amplitude. Okay, no fluctuations. If I take this, essentially it is depositing some amount of energy. Let's say this EM wave is incident on a photodetector. So you are depositing some energy into the photodetector, and that energy causes the electron hole pairs to be generated, the photoelectrons, right? So first you have the EM wave incident, then it interacts with the material and then generates electron hole pairs, and then they will separate and then it gives the current. That is a photodetection process, right? So now if you consider this, the probability of generating a photoelectron in response to an incident field is itself Poissonian. So we are not really going into the details, but what I'm claiming is, even if I have a perfect electromagnetic wave like this, classical electromagnetic wave, constant intensity, if I look at the photoelectrons that are generated, there's a certain probability of generating n electrons in a particular time interval, right? So this Pn I'm representing as probability of generating n electrons in a time interval, in delta t. Okay. If I look at that probability and I calculate it, we are not doing all that, but just take it for now, that in the time interval, the probability is going to be given by n bar to the power of n exponential minus n bar divided by n factorial. So this itself, the photo detection process itself exhibits a Poissonian statistics. Okay. This is Poissonian, right? So what we can conclude from here is, if you are, let's say, observing Poissonian statistics in the detector, it does not mean that your source is quantum. So the observation of Poissonian statistics, right? Of Poissonian statistics is not a proof of quantum nature of light. Why do we say that? Because even if you take a classical electromagnetic wave, I'll still get Poissonian statistics from the photodetector. But the interesting catch here is that if you observe Sub-Poissonian statistics, then that is a proof, right? Because you cannot replicate that with a classical electromagnetic wave. Classical electromagnetic wave will give you Poissonian, but if you observe Sub-Poissonian then statistics, that implies cannot be explained by the photodetection process. Okay, so cannot be explained by classical theories. So it is definitely quantum phenomena. Cannot be explained by classical theory. So if you observe that, it is very, very interesting. Now, when we say photodetection, what is the process involved? We said that, okay, there are these photoelectrons generated. How many electrons are generated? Because finally a photodetector will give you output as a current. What is the current that you get out of a photodetector? That can be computed. What will that depend on? Let's assume that, let's say there is a photon flux, right? We know how to calculate the photon flux. The photon flux is given by, we said power by the energy, right? So if you have a photon flux, let's say there are 10 photons per second, and they will generate, let's say, 10 photons. That means there is perfect quantum efficiency, right? So in effect, the current is going to be determined by the number of electrons that are generated in response to incident photons. So basically that number of electrons will be quantum efficiency eta times the charge of electron times the number of photons. This is going to be power by h cross omega. So when you have, let's say, n number of photons coming in, if all of them are generated, then you basically have E, right? E is the charge of electron, and then charge per unit time gives you the current. So this eta factor is telling us what is the efficiency, quantum efficiency. For every 10 photons, how many electrons are generated, let's say. Okay, that is the quantum efficiency. So quantum efficiency times electronic charge will give you the charge. And this is number is already there, power, right? Number of photons. So that is equal to number of eta times number of photons will give you the number of electrons into charge divided by time will give you the current, right? So this is charge per unit time. Okay, coulombs per second. So current, right? Some amps. This unit is going to be amps. Okay. So this is how the photocurrent is generated. Now, when I have photocurrent generated, one of the important properties of a photodetector is what is known as responsivity. Okay, responsivity, by which we define as, let's say, the current divided by the incident power. If you have, let's say, 1 watt of power incident, how much is the current that you're generating? How many milliamperes or amperes you're generating, right? So that is what is known as responsivity, and that is clearly is going to be equal to eta times E divided by H cross omega. So if you have a responsivity of 1, essentially you have very, very good detector. Typically the responsivity will be smaller, right? Rather, responsivity will be some amperes per watt. Okay. So now, once you have this, what will happen if you have, let's say, some fluctuations in your incident photons, number of photons, right? There is some fluctuation. How can we detect the fluctuations? Well, your current that is emitted, or current that is generated from the photodetector, let's say I of t, is going to be having some mean value, which I am representing by angular brackets here. So angular brackets of I means mean value of current plus some fluctuations, delta I, which is a function of time. Okay, this is how the current generated from the photodetector is going to be, and schematically that is shown here. So you have some mean value here, and there are some fluctuations with that. Okay, now if you have that fluctuation, that is essentially noise that we are generating, right? So what is the noise power that is present in the noise? From simple analysis, we can actually conclude that the power, noise power, P noise, let me say, is going to be equal to 2E delta F R. Sorry, power is going to be, I'm writing the full expression. Let's go step by step. Instead of this, so there is this fluctuations that are there. So that is going to be delta I square times RL. If you have some load resistance RL, the total amount of noise power is going to be delta I times RL. And you can show that delta I is essentially equal to 2E delta F times mean current times RL. Okay. This we are not really proving. We are just giving this expression saying that, okay, this is going to be my noise power. 2 times the charge of electrons times the bandwidth, and then average current times RL. Okay. So now we want to look at how the noise behaves as a function of frequency. Okay. And that is shown in the bottom picture here. What we are saying is this is a frequency. If you look at the spectrum of the noise, okay, if you look at a spectrum of a sine wave, you get a one sharp line like this. But now we are looking at spectrum of the noise. The reason we are looking at it is we want to see what are the components that are present. And it turns out that in the low frequency regime, you will have high noise, which is actually because of all the, things like classical things like, let's say the vibrations, okay, and the temperature variations, right? They all give you some noise, okay? So you have noise which is higher than the, which is high, but as you go to higher frequencies, these vibrations or temperature variations, they occur over a very, very long time period, right? So that they will not contribute. And at high frequencies, you will end up with what is known as short noise. Short noise means you essentially have photons which are incident, like shots of photons are coming in, and there is some, let's say, some current that is produced, some noise level. So short noise is essentially a signature of the intrinsic statistics that are present, right? I mean, it could be the statistics in the photodetection or the source, but the statistics of one of those processes translates to short noise. And if you go to even higher frequencies, it turns out that the detector itself will have some response time. So it will not respond beyond a point. Here 1 over tau d is the detector response time. So if you go to much higher frequencies, this will not respond. So essentially you'll end up with short noise. Now, if we are able to measure short noise, let's say at high frequencies, right? Measurement of short noise gives insight into photon statistics. Okay. So what sort of insight? We will just come to that in a moment. Before I go into it, I just want to take an example problem so that you are comfortable with this. So what I want to do is calculate this. So let's say you have a 10 milliwatt helium neon laser, which is operating at, let's say 632 nanometers, and it is incident on a photodiode with some responsivity, which is given here. So 10 milliwatts, 632, and then there is a responsivity of the detector, and there is a load resistance. Okay. So first question was, what is the quantum efficiency of the detector? Sorry. Okay, yeah, if you want to determine the quantum efficiency, we know the responsivity, right? So the responsivity is given by what? Responsivity is going to be equal to, first if A, the responsivity is going to be eta times E divided by H cross omega, right? So wherein, excuse me. So this is given responsivity, so 0.43 ampere per watt, that should be equal to eta, which is a quantum efficiency, times charge of electron, I leave it as it is, divided by H cross omega. The reason I'm doing that is H cross omega in EV, I know how much it is, right? So if I have 632 nanometer light, the energy of the photon is going to be E of lambda, E of photon is going to be 1.24 divided by 632 in microns, so it's 0.6328. That will be roughly something, I think it should be roughly 1.9, 1.95 or something. Okay, this should, because 128, right? 630, yeah, 1.9 something, 1.93 or something. Okay, 1.9 EV. This is my responsivity of the, this is my energy of the photon. So now, so this is going to be equal to eta EV, right? So when I have charge, it will cancel out. Essentially, I'll get 1.9 here. So my eta is going to be 1.9 times 0.43. And that will turn out to be roughly about 84% here. Okay, that is my responsivity, my quantum efficiency. Okay. Now the second question was, what is the average photocurrent? Average photocurrent we saw was simply going to be determined by responsivity. Once you know the incident power, you know the responsivity of the detector, you can calculate the average current. So current is going to be simply the responsivity, which is 0.43 times power, incident power, which is 10 milliwatts. So in this case, I have 4.3 and 10, so 4.3. So 4.3 milliamps is my current. All right. Now, the third part is, what are the current fluctuations within a bandwidth of 100 kilohertz? Current fluctuations is basically delta I, right? Delta I square. Delta I square. I said is basically equal to 2E delta F into mean current. So delta I square is equal to 2E delta F into mean current. That's equal to 2 into 1.6 into 10 power minus 19 into delta F is basically 100 kilohertz here. The bandwidth is 100 kilohertz. So 100, I'll write simply 10 power 5 into mean current is 4.3 into 10 power minus 3. Okay. If you calculate this, it will be some number, something in the range of 18. Okay. So it will be 10 power minus 19 plus into 10 power 5. So 10 power minus 14 minus 17. Well, something in the range of 18. And I think if you do this, it will turn out to be something like 12 nanoamperes. Okay. It will be that. You will see that. This is current, not current square. So delta I is going to be about 12 nanoamperes. The question was, so basically your fluctuations in the current are dependent on the bandwidth. So if you look at it here, if you take a large bandwidth, then the fluctuations in the current is going to be large because the classical part is included, or maybe if you're only doing it high frequency, then only the short noise is going to be. So there's going to be difference in the noise, in the current. And that is true. And that is why when we do electronic measurements, we always want to measure in the, we try to have a bandwidth limited case because we don't want noise in the other parts to actually contribute. So for example, I have if you have, let's say, a signal at 1 kilohertz or let's say 10 kilohertz, okay, our modulation, let's say you're modulating a chopper or something, you're modulating a laser by using a chopper, you get a signal at 10 kilohertz. Now, you want to actually put a band pass filter, only let the 10 kilohertz pass. and filter out all the other noises. So we want to measure that, because otherwise if you take a wide bandwidth in your detector, before a detector you put a broad, all the frequencies are allowed, then your signal to noise ratio is deteriorating, because you are adding up noise in every frequency range, and then signal is only one place. So in measurements, it's actually useful to have bandwidth limited cases. So we have to choose that. So basically, if you go to extremely sensitive measurements, we use things which are called as lock-in low noise amplifiers, which can have low pass and high pass filter set, and so you only in certain frequency range you pass your input, and you can get much more sensitive detection. If you simply don't use anything, then you are actually getting all the noise up to the from 0 to whatever detector response. We don't like that. So that's why we are saying that, of course, if you reduce the frequency range, instead of 100 kilohertz, I choose 10 kilohertz, my noise is going to reduce. Noise floor is reducing, yeah. So that's very important. What is the measurement frequency range? You're essentially integrating, right? Yeah. Or rather, in this case, you're looking at fluctuations anyway. All right. Okay. So, yeah. So that's why here I think the noise is about 12 nanoamps. And then you can also have a situation where the fourth one is noise power in dBm after amplification. So noise power now is what? I square into RL, right? Delta I we have calculated already. So P noise is going to be delta I square RL, right? That's what it should be. And that is going to be equal to 12 nanoamps into RL is 50 ohms. 12 into 50? 6 something. Yeah. And then, yeah, you can calculate how much it is. Okay. I think it will turn out to be some 10 power minus 15 watts approximately. And now, if you have such a scenario, and the question was basically to calculate in dBm after amplification of 20 dB, with a power gain of 20 dB. If you say power gain of 20 dB, it translates to basically you are increasing it by 100 times. So after amplification, you have how much? P noise is going to be equal to 10 power minus 13 watts. And in dBm, that will translate to how much? Minus 91, will it? No, I said 10 power minus 13, so 10 power 10, so roughly 100, minus 100. No, I mean, you have to calculate exactly. I didn't do the exact calculation here. So roughly, this is going to be roughly minus 100 dB. Okay. So this is yeah. So this is how photo detection happens, and it actually is quite important to understand the details of it if you are working in the low noise regime. Okay. So always remember, why did we do all this? We are doing this because we want to study the statistics. And initially when we talked about it, when I introduced, I said that the detector if you are looking at it as a photon and you are counting the number of photons using, let's say, a very, very sensitive detector like an APD or a PMT, it has a dead time of about microsecond and we cannot go beyond that, so you cannot count. But we don't want to be limited by it. We want to look at ways, we are trying to look at ways by which we can actually detect below that, or rather at intensities higher than that. Because if you have that extremely sensitive detectors, we can't do anything. If the intensity level is more than a few hundred picowatts or something, you cannot measure. So if you want to look at it, let's say in 100 microwatt regime, you have a lot of photons coming in. Is there any way to look at that? And what we are saying is, yes, there is. It's a little bit tricky process. But let's say if you have a photo detection process, the current fluctuations will correspond to the photon number fluctuations. And that's, we want to look at the current fluctuations and try to determine something about the statistics. That's the whole goal. Okay. So one of the key issues here is the noise. So we want to reduce the noise. So basically to reduce the noise, so far we have seen one approach. So let's say to reduce noise, the first approach we have seen is work at higher frequencies. Okay. Work at higher frequencies where 1 hour of noise is absent. 1 hour of means that classical noise I said, no, initially there is this high noise and then it drops as a function of frequency. 1 hour noise is absent. This is one approach. But sometimes, your detectors are slow, and then you can't really work in very high frequencies because the detector response time also is important, right? So if you cannot do that, the second approach is basically to use what is known as use balance detection. Okay, what do I mean by that? Let's say instead of using one detector to detect a photon or a photon stream, use two detectors. Because the detectors are identical as possible. Okay, now have an incident beam and use a beam splitter to split the beam into two sections, one transmitting and one reflecting beam. Once you have that, this falls on this PD1 and PD2, which are identical photodetectors. Once you have an identical photodetector, then I'll take the photocurrent that is generated from each of them, I1 and I2, and then I subtract them. When I subtract, the interesting thing is all the common noise factors, like classical noise, which is common due to external factors, gets all averaged out. Okay, so what you're left with is essentially short noise. Okay, so that's one way where actually we can try to measure at the short noise limit. Okay, and a practical implementation of the circuit could be something like this here. So let's say you have two photodiodes and you apply voltage, V0 and minus V0. If you do this effectively in this point here, it should be close to center. Voltage is going to be close to 0, and provided the RL is not very large. So in that scenario, the current that you will measure is going to be I1 minus I2, the photocurrent 1 minus photocurrent 2. And these diodes are reverse biased deliberately so that they work as a more efficient photodetectors. From the photodetector theory, you know that. So if you have this sort of a current which is difference, then I'll pass it through a capacitor and an amplifier. So essentially what my voltage output here is going to be, this V is going to be proportional to current fluctuations. So if I look at how the photocurrent is behaving, I can study that. Okay, and this is a very important technique that we use in the measurements. All right. So we are able to study the photocurrent fluctuations, but we initially said that the photodetection process itself is going to exhibit Poissonian statistics. So we cannot claim that we have a Sub-Poissonian source by looking at it. Sorry, we cannot conclude about the statistics of the incoming photon beam. But suppose you are able to measure photocurrent fluctuations lower than the short noise limit. What does that imply? How can that come? I'm having a perfect classical source. I'm shining it on a photodetector. When I do that, I'm getting the short noise, which is the detectors, fluctuations that are created by the photodetector, right? Now, if you are actually going below that, that is a signature of basically a quantum source. The fluctuations are actually smaller. Okay. So now one of the experiments that was done is here in this case, they have taken a battery and then you excite an LED, which is a high efficiency LED here, through a resistor. Resistor is simply there to control the current that flows through the circuit and then amount of current photons that are generated. And we ensure that basically this voltage drop across R is greater than 2 kBT. If we meet this condition, it turns out that basically, this condition is necessary to make sure the short noise is greater than thermal noise. If you make sure of this case, then we'll see that you have this light which is generated now, because we use a battery here instead of a regular power source. Power source will actually, let's say if you connect it to AC mains, that has some noise, 50 hertz noise. So battery will eliminate that, DC, right? So minimize power supply noise. If you do that and you have photons that are generated from here and you look at the statistics, it turns out that in this picture, this is an experiment which was done wherein you see the short noise limit, which is this dark one. And then this is the photocurrent noise, the dark one, and the short noise limit is shown here on the top. And you see that you are actually measuring noise levels below the short noise limit. And that is an indication of basically a Sub-Poissonian light source. Okay. So it's a bit tricky because, what's the point of having a a source which is, I mean, it's very, very sensitive. You can't even modulate and so on. So there are some issues with this, but this is one of the simpler way of figuring out whether you have Sub-Poissonian statistics or not. All right. Actually, ideally, I guess this is already balanced detection. I'll have to carefully look at the source. I mean, this is from this book, but I think this should be a balanced detector because you're not seeing the 1/f noise here. More or less, it's flat. That means it's a balanced detection scheme. It's schematically illustrated like this, but there are a lot of details involved in this. Okay, then you see that it is lower than the short noise. That means, short noise, lower than the short noise photocurrent noise. So that means we can conclude that it is emitting in the Sub-Poissonian range. The question is, we are using an amplifier. Doesn't it add? Well, it does. So if you want to do that, we'll have to have specialized amplifiers, which actually even have additional DC power source inside. They have a battery. You switch off, you disconnect it from the mains and you run it on the battery so that it adds minimum amount of noise. Low noise amplifiers, we call them. We don't add noise through that. We have to be careful about all this. Yes. So actually, this is a very tricky process because how do you make sure that you eliminate everything else and actually see it? So it's not that simple. All right then. Yeah. Let me stop here. So we'll continue in the next lecture. Thank you.